in this lecture I will show the use of Fourier transforms in solving partial differential equations. I will take the example of partial differential equations, but you can use it for any differential equations. In the last lecture what we saw is that if we had f of x whose Fourier transform was f tilde of k, and you had g of x equal to df by dx, okay, of a derivative, then what we had was that we saw that g tilde of k was equal to I k times f tilde of k. Suppose you had a second derivative, okay. Suppose you had h of x is equal to d square f by dx square, then h tilde of k, you can show that this is just I k square f tilde of k, that is equal to minus k square f tilde of k, okay. And in general if so every derivative introduces a factor of I k. So, if you take n derivatives you have to introduce n factors of I k. Now one of the things about Fourier transforms is that it should be absolutely, your function should be absolutely integrable. So, condition for existence of Fourier transform is f of x should be absolutely integrable. In other words, your integral f of x, absolute value of x dx from minus infinity to plus infinity should be less than infinity, okay. It should be finite, and this can happen only if limit as x tends to infinity f of x tends to plus or minus infinity f of x equal to 0. So, if your function does not go to 0, okay, then you can clearly see that the area under the function, okay, will go to infinity, okay. So what I want to emphasize is that Fourier transforms are natural methods for solving problems where function goes to 0 at infinity. So, what I mean is, suppose you have a differential equation, let us take an example. So, suppose you had an equation d times dou square c by dou x square equal to dou c by dou t, okay. And here you have this is called a one dimensional diffusion equation. The conditions are minus infinity less than equal to x less than infinity, and t is greater than 0, greater than or equal to 0. And this partial, so this is a partial differential equation, it is called the one dimensional diffusion equation. Minus infinity is less than x less than infinity, t has to be greater than or equal to 0. Now, the boundary condition c of 0, okay, c is so remember c is a function of x and t, okay, c is a function of x and t. So, boundary condition I can write c of x 0 at t equal to 0, okay. This is some function, I will just call it g of x, it can be any function g of x. So, with this boundary condition can we solve this one dimensional diffusion equation, okay, and this will illustrate a lot of interesting properties of interesting things that come with Fourier transform. Now, notice that this also c of infinity equal to infinity at any time minus infinity at any time equal to 0. So, basically as x tends to infinity, as you go very far away in space, okay, the C is typically the concentration of some species, and that goes to 0 as when you go very far away. So, typically the kind of problems that we look at are those in where you start where you might start with some initial concentration. So, this might be C of x t, and what you will have is that concentration will spread out as t goes to infinity, as C of x t prime. Okay. So, t prime is greater than t, it might look as something else, but basically it goes to, what I wanted to say is that it goes to 0 at infinity. So, such equations are naturally solved by Fourier transform. So, this implies that you do a Fourier transform x variable. Okay. So, you do a Fourier transform of x variable. So, there are two variables x and t. So, you leave t as it is and do Fourier transform of x variable. So, now let us get back to our equation. So, our equation d times dou square c by dou x square equal to dou c by dou t. Okay. Now, if I do Fourier transform, okay, now Fourier transform of derivative is nothing but, or let me, yeah. So, if I take Fourier transform on both sides, then I can see that Fourier transform of second derivative is I k square, and now I have c tilde of k and t, this is equal to c tilde of k t dou by dou t. So, what I get is a differential equation in time. Okay. Now I can solve this differential equation in time. Okay. So, I can write dou c by dou t is equal to minus k square d c. Okay. I can write c is equal to, or c of c tilde of, put a tilde here, of k t is equal to c tilde of k 0 e to the minus k square d t. Okay. So, this is the solution of this differential equation in time. Okay. And this is the constant of integration I have put as a prefactor to this exponent. Now, c tilde of k 0 is, we had a boundary condition c of x 0 was g of x. So, c tilde of k 0 is nothing but g tilde of k e to the minus k square d t. G is some function of k. Okay. So, g is some known function of k. So, you are told some function. Okay, that depends on whatever initial condition you take. I should say this boundary condition is an initial condition. So, this is the solution. Okay. So, we have c tilde of k. Now, if I wanted to take if I wanted to calculate c of x t, okay, this is inverse Fourier transform of this. Okay, inverse Fourier transform of this. So, I just go ahead and calculate it, 1 over root 2 pi integral. What I want is the inverse Fourier transform of g tilde of k times e to the minus k square dt e to the I k x dk. Now, what you are doing is you are taking the inverse transform of a product of functions. So, we are going to use the convolution theorem, but first let us find the inverse Fourier transform of e to the minus k square dt. So, what is inverse Fourier transform of e to the minus k square dt? Okay. And this we can use our result for Gaussian. Okay. So, this is basically, this is equal to e to the minus dt into k square. Okay. This is a Gaussian. Okay. And we know the Fourier transform of a Gaussian. Okay. So, we just go to our Fourier transform pairs. So, let us just go back to the first lecture of this module, where we did the Fourier transform for Gaussian. So, what we said was that if I had e to the minus alpha k square, okay, then the Fourier transform is 1 over square root of 2 alpha e to the minus x square by 4 alpha. Okay. So, now instead of alpha I have d times t. So, I should have 1 over square root of 2 dt e to the minus x square by 4 dt. So, I just have so this Fourier transform. So, it will be 1 over square root of 2. Now, alpha is dt e to the minus x square by 4 alpha square. Alpha square is dt square. Yes, 4 sorry not dt square, x square by 4 dt. Okay. So, this is the Fourier transform of this, and now what we get is that we can write c of x t. Okay. Now, we can use the convolution theorem. Okay. So, by using the convolution theorem, what we will get is that if you let us go to the convolution theorem. Inverse Fourier transform of a product of f tilde g tilde is 1 over square root of 2 pi times the convolution. So, if I take this product that we had, so c tilde of k t was a product of g tilde of k and this e to the minus k square dt. So, we have the inverse Fourier transform of this. Okay. So, let me call this h of x. Okay. So, this is just 1 over square root of 2 pi g star h of x comma t. Okay. So, this is 1 over square root of 2 pi. Okay. Now, I will write it as g of x minus x prime times 1 over square root of 2 dt e to the minus x prime square by 4 dt dx prime from minus infinity to plus infinity. So, this is the solution. Okay. So, I mean this is an integral. If you know this function g, you can perform this integral, and what we have shown is how you can solve this partial differential equation using the method of Fourier transforms. Okay. And we solved it for an arbitrary g. Okay. So, this is the solution for arbitrary g. Okay. Now, let us look at an example. Suppose suppose g of x is equal to delta of x times, let me call it C0 times delta of x. C0 is a constant. Then you can see that c of x t is equal to, so let me take the 1 over 2 square root of pi dt, and what I have is integral minus infinity, and I will take the C0 outside, minus infinity to plus infinity. Now, what I have is delta of x minus x prime e to the minus x prime square by 4 dt dx prime. Okay. So, now integral over the delta function of some function is just the function evaluated at x prime equal to x. So, this just becomes C0 by 2 square root of pi dt e to the minus x square by 4 dt. So, now this is the solution. So, what does this solution mean physically? So, the physical interpretation of this solution is the following. So, what you have is you have, let me show x here, and you have c of x t. So, at t equal to 0, c of x t is g of x, which is a delta function in x. So, at t equal to 0, it looks like this. C of x 0. Okay. Now, as t increases, okay, it becomes a Gaussian. Okay. Now if you take this Gaussian and put t equal to 0, then then you basically the limit of this Gaussian as t goes to 0 is the delta function. Okay. So, as t becomes larger, okay, this Gaussian goes its width as t becomes larger, the width of the Gaussian becomes more. Okay. So, your Gaussian becomes a wider function. So, as t becomes larger, okay, and this is c of x t. As you increase t, it gets wider and wider, c of x t for larger t. And you can also see that as t goes to infinity, your Gaussian. So notice that the prefactor also is inversely proportional to t. So, as t becomes very large, your prefactor becomes very small. This becomes e to the 0 almost goes to a constant. So as t goes to infinity, your species basically spreads like this all over. T tends to infinity. So, basically it goes to a constant. So this is a nice illustration of the use of Fourier transforms to solve. Okay. So, what you have is initially you have some species, might be let's imagine that you have some species that is there only at x equal to 0. So, that is there only at a particular point, and what we are seeing is how this species spreads in space as time increases. Okay. So, this is what the diffusion equation says. So, suppose I imagine that I take a perfume bottle and I open it. So, at t equal to 0, all the perfume at the initial time, the perfume is all localized in one region. Okay. But as t becomes larger, this perfume will spread. Okay. And so, this is a one dimensional spreading that you are seeing through this diffusion equation. So, I will conclude this lecture here. In the next lecture, I will mention about some other integral transforms, okay, such as the Laplace transforms, and I will just mention how they can also be used to solve differential equation, and in which cases you should use Laplace transforms, which cases you should use Fourier transforms. Okay. So, that will be the next lecture of this module. Thank you.